Okay, here we go. So last time we had just gotten around to defining double integral. Well, just entering the section on double integrals. We actually did not yet actually define double integrals. Why are we doing this? Recall we spent a little time talking about how you can use something called an iterated integral to compute volume. Right? And, in single variable calculus, the formula that allowed us to compute how much space there is under a graph also allowed us to compute tons of other things. And so we speculated on the basis of that and hoping the pattern would continue that maybe we'd be able to compute tons of other things with iterated integrals as well. And, nope, doesn't work. Right? As an argument, it doesn't make sense to talk about for example, mass per unit area times length, and then make a case for our understanding of that quantity and how it behaves, and then I can accumulate it and view it as the whole as the sum of the parts. I don't know. I can't do any of that stuff because I don't know what this means. Right? It's not a natural quantity. So what we're going to find, this new thing that we're going to define called a double integral, is going to be the solution to that problem. Before we get into that, real quick reminder, and I know I spent a bunch of time on this last time, and I'm going to try not to spend too much time on it this time, but the definition of a single variable integral is a Riemann sum. Common misconception about Riemann sums is that it is an outdated, inefficient computational tool. And that is not true. None of that is true. Riemann sums serve a very different purpose. Namely, the fact of Riemann sums is how we make connections from applications to integrals, which of course we can then compute with the fundamental theorem of calculus. So for example, I can take an application question like, mass of a rod or something like that, and I can say, hey, the whole is the sum of the parts. That's perfectly reasonable. I can talk about mass per unit length times length, computing the mass of a little slice, a little piece of my metal rod, one-dimensional rod, and then I can add those all up. Right? So Riemann sums make perfect sense for that application. But if you try to make a direct case for why mass is area, doesn't work. It's just not clear why should mass of a one-dimensional thing equal to area of a two-dimensional thing. Any actual argument that does that is, in fact, a sloppy, indirect Riemann sum argument. Right? So again, it remains there is no argument there. Okay. All right. So let's keep all that in mind. We are now going to move along to trying to do the same sort of a thing in two dimensions. Like so in single variable calculus, again, you take your domain, namely an interval, you chop it up into little pieces, and you argue that the whole is the sum of the parts. If our domain is two-dimensional, if I have something that is distributed over an area, not over an interval, what would it mean to chop that up into little pieces and say the whole is the sum of the parts? Well, chopping it up into little pieces would give me little sub-rectangles like this. Right? On that sub-rectangle, I can do lots of different things. I can say the amount of mass in here is mass per unit area times area. Cool. If this were Wyoming, and I wanted to compute the population of Wyoming, and then I'm looking at one small little region in Wyoming, people per unit area times area would tell me the number of people in this little sub-rectangle, right? Etc. All this stuff fits perfectly. Makes perfect sense. So this construction right here, multiplying some sort of a density times the corresponding area, so like mass per unit area times area, people per unit area times area, whatever, makes perfect sense on little pieces. And then you can say, all right, well, I just want to add all those up over this entire thing, over all of Wyoming, or over all of the metal sheet that I have, or whatever it is that I'm adding up. And that gives me the total. So, big picture, before we get into the details, does that all seem reasonable? Anybody have any questions about the whole sum of the parts? Okay. All right. Okay, let's talk details. Notice that as I slice up, like so. And then later, as I slice like so, let's see if I can do this well. Now, as I slice up my domain into little pieces, such as that, note that among other things, I am also slicing up the interval from A to B. And slicing up the interval from A to B, we already did that. We did that back in Calc 1 classes, right? And so delta x and x sub I is a plus I delta x. All those details are established. It's the same story here. We have an interval from A to B. We're chopping into n pieces. Old news. Okay. So now we just have to add in that we're doing the same kind of thing over here on the y-axis from C to D. We are slicing that up. Again, the same sort of deal. As we did the horizontal slices of the rectangle, we are also doing slices of that blue interval on the y-axis. And slicing up an interval, same deal. I mean, different details, right? Here we're going from C to D instead of A to B. So we have a different formula for delta y. And likewise, we're going to have a different formula for, these points over here that I'm going to call y sub j. But structurally, it's the same approach that we did back in Calc 1. Now, one little detail I do want to comment on is the index. We use I, right? When you're talking about x, all these different x endpoints, in our subintervals down here, we use the subscript I to keep track of which one of those we're at as we move across. So, well, if I has already been used to be an index on the x-axis, I have to pick a different index on the y-axis. We're going to use J, right? It seems like a natural choice, whatever. It's just a letter. It doesn't matter. Okay. But there's the details. Right? And now, if I say chop it up, add it up, or the whole is the sum of the parts, whatever you want to do, whatever you want to call it, on each little piece, we have a simple question of quantity per unit area times area, and then we add up over all the pieces. Take a limit to make those round off errors go away, and we are all good. Okay, so this is a strategy. We're going to see some examples in a minute, but this as a big picture strategy, the chop it up, add it up strategy, the whole is the sum of the parts strategy, this is kind of how that's going to work and all the relevant details. Okay, so let's make this formal, make a definition. This expression that we just got through motivating, this strategy, this chop it up, add it up strategy, we're going to give it a name. We're going to call it a double integral. This is not single variable calculus. This is a brand new thing. In single variable calculus classes, you will not have seen summations with two indices. It's not a thing, right? Now, by contrast, if you go back to the iterated integrals that we talked about previously, here we go. Iterated integrals, right? This thing on the inside, literally a single variable integral. I mean, you have to know that you're viewing one of the variables as constant, blah, blah, blah. But it's a single variable integral. It's a regular old Calc 1 Riemann sum. And then once I know what that is, the integral on the outside, another single variable integral. So arguably, iterated integrals are kind of just, they're mostly single variable calculus. They're barely multivariable calculus. Not so with double integrals. Double integrals, brand new concept. So we do need then also a brand new notation, and that's this right here. I want to emphasize this is just notation. Think of this as a shorthand. And in particular, the way I like to think about it is that this is just a shorthand representing that delta x, delta y is our notation for representing a little piece of area. So dA, differential little piece of area. And then likewise, this little symbol right here is just a shorthand for this statement that, look, I'm going to add that up over my entire rectangle and take a limit so my round off errors go away. Is that cool? Anybody happy? Okay, just notation. So that said, whenever you see one of these right here, what you should think to yourself is, this is just a shorthand notation for a Riemann sum. And this is what you're actually doing. That's an actual thing. Riemann sum is an actual prescription for a computation. This is just shorthand convenience to represent that. Okay. All right. Now, real quick, all of the different variations of how to define double intervals, and there are many, are unnecessary for what we're doing in this class. So I've given us the easiest formula. It's perfectly good enough for what we're going to do. In fact, all the different complicated variations, such as using irregular partitions and using different arbitrary test points within the subrectangle, these little details are useful for other things. If you're doing real analysis, if you want to prove the theorems that we're going to be using, sort of in practice in this class, then yeah, you need to worry about that stuff, and it's all important, and it's beautiful mathematics, and that's not what this course is. Though this course, we're just going to go with this one definition, and it's fine. That said, the book does use these two things here, and you're not responsible for that. So I believe this is noted on the content syllabus as excluded material. So heads up, don't worry about the irregular partitions and such. Okay. All right, so let's do one. Let's compute the volume under a graph. Oh, wait, we already know how to do this? Oh, yeah, question.
Yep. For the bounds on the double integral,
yep.
We have questions that have the bounds as functions rather than just constants.
So thank you for reminding me that I need to talk about the domain. So this little subscript right here is just a shorthand notation for the rectangle over which I'm computing this double integral. You just make it a subscript and then indicate elsewhere what the details of the rectangle are. For the moment, we're only talking about rectangular domains. But we are soon going to talk about non-rectangular domains, and I think what you meant by bounds being functions, we're going to find that when you have a non-rectangular domain, then yeah, functions get involved in a way, but that's you're getting ahead several pages. Yeah, totally. For the moment, only rectangles. Okay. All right. So, yeah, volume under a graph. We already know how to do this. Volume under a graph, iterated integrals. We already have an answer to that question. Why are we returning to this question? Well, because our answer to this question was very limited. It only worked for just this one thing, just volume. It only worked for volume, and we want to have tools that work for other things, and so iterated integrals are kind of a disappointment, frankly. And so we're going to take a different approach, hoping that this will apply more broadly, and it does. So just as a starter example, though, if you wanted to compute this volume over a given rectangle, I argue that the whole is the sum of the parts. The whole volume, that is, I can think of as the sum of these little volumes. Right? The grand total volume here is the sum of the volumes sitting over these little sub-rectangles. In other words, I've taken my blue rectangular domain down here, chopped it up into a bunch of little sub-rectangles. Sitting over each sub-rectangle, there's a little French fry thing here. Right? And the volume of a French fry is really easy to write down. It just has a rectangular base, and then it's got a height. And so height times the area of the base. And so there you go. Easy to write that part down. Is everybody good? Now then we want to add that up over the entire domain. So I'm going to add up over the entire thing here. So summation. Right? And then you notice that, oh my gosh, this is exactly a Riemann sum, aka it's a double integral. How are we doing? Yes?
Why does this look so similar to the 2D version you showed us? Because it's still delta x, delta y. I don't understand that in 3D now.
Yeah. Yeah. So what I was drawing here is just the domain.
Oh, okay. So that was part of...
Yeah. So what you're adding up, what it is that's distributed over this domain is going to vary from application to application. You might have mass per unit area or people per unit area, what have you. arguably here, the height, this F being this height, you can think of height as being volume per unit area. Yeah. So, that's right. This is just, the picture's three-dimensional because the application we're applying the double integral construction to happens to be three-dimensional. Is that all right?
Yeah.
Cool. Okay, so as predicted, double integrals, very nice construction, and it reproduces in some sense an answer to an old question. Now that fact is actually really useful. Again, previously we computed volume with iterated integrals. We did that last time. We have just now computed the exact same volume with a double integral. And because we've computed the same thing two different ways, these two results are actually equal. And far more important than the fact that I can compute volume with either one of these formulas is the fact that double integrals, I see now, can be computed with iterated integrals. That's going to be a big deal. So let me talk through why that's a big deal. I do this with a diagram. I like to think of this as a strategic diagram. We've talked about various different questions and quantities and constructions and relationships. We've done a bunch of stuff. This is a kind of a strategic summary of all that business. We started off by asking, hey, how do I compute volume under a graph? We wrote down an iterated integral, which we compute with the fundamental theorem of calculus. So I'm going to say this part of the diagram was what we did first. The frustration we have with this business is that it's kind of done. We can't do anything else with it because, for example, mass is not volume. Right? I can't just assert out of nowhere that, you want to compute mass distributed over a region? Well, I claim it's a volume. Right? Why? Where would the volume of what? Why would it be a volume? Doesn't make any sense. And you furthermore can't take a mass question and immediately argue it to be an iterated integral. That's where we ended last time. Right? The units kind of don't work out. Any attempt to do this, to write mass directly as an iterated integral, you're going to find yourself talking about mass per unit area times length. And it's a mismatch. You get a concept that we don't have any intuition for. You can't make arguments about how it accumulates or whatever. It's just, you're done. It doesn't work. Okay, so with the understanding that you can't do either of these connections, we're stuck until we create, as we just did, the idea of a double integral. Right? And we could then we argued that double integrals can compute volume. We recall that we had previously seen that iterated integrals compute volume. I then pointed out it was going to be valuable that double integrals are therefore equal to iterated integrals. And now we're in business. You can look at this diagram as it stands here, and we can see the path that gets us from an application question that we're interested in to the numerical answer that we're hoping for. And the path is a 3-step path. Step 1, turn your application into a Riemann sum, aka double integral. Step 2, rewrite your double integral as an iterated integral. Step 3, compute your iterated integral with the fundamental theorem of calculus. So again, this is the 3-step process that gets us from real world, actual, rubber meets the road application questions and turns it into answers, numerical answers, namely, how long do I cut this piece of wood to fit my application, right? The actual nitty-gritty answers. Is everybody with me? Okay. So notice in the same way that, I made the case for single variable integrals that area under the curve was a curiosity and a convenience of intuitive convenience, I suppose. It didn't really actually serve a purpose. Same thing here with volume. It's not involved in this 3-step process. If I've been asked to compute the number of people in Wyoming, right? Double integral, iterated integral, answer, volume didn't come up. Volume is not part of the reasoning that gets us the answer to that question. I guess it's geometrically satisfying, and again, it's good for visual, geometric satisfaction. But that's all kind of personal, right? It's not actually part of the argument. Okay. All right. So, whoops, I erased the wrong deal there. I'm going to show you an example, 3-step process in action momentarily. I do want to point out, by the way, you do have to give me all 3 of the steps. Again, I know I say this a lot, but I say it a lot because it's true and it's really important. This class is not about the answer. This class is about the reasoning, right? So the reasoning is the 3 steps. That's what I want to see. And the answer that you get to at the end, yeah, it's nice. Okay, but the answer independent of the reasoning is not what this class is about. So again, I know I say it a lot, but it's very important that you actually give me all of the reasoning, all the steps of the reasoning. Here we go. Real world example. Suppose I have mass distributed across a rectangular sheet. There's my rectangle. Don't forget this notation that we have describing a rectangle. Suppose that mass is distributed across the area with this density function. So this again gives me mass per unit area as distributed across that area. And here's my 3-step process. Step 1. First I observe mass accumulates. The whole is the sum of the parts. Chop it up, add it up. Say it however you like. But the whole is the sum of the parts. Pretty satisfying. Second, mass is mass per unit area times area on each little piece. Easy argument on the little pieces because density is approximately constant there. And then I notice, oh my gosh, check it out. I've got exactly a Riemann sum. Cool. Riemann sums are integrals by definition. Okay, so step 1, mass is this double integral. How are we doing? Yeah, question.
The delta is density.
One more time.
The delta density.
Yes, that's right. This right here is density. This is mass per unit area. That's right.
Oh.
Yeah. So this is the lowercase Greek letter delta, right there. Yeah. The uppercase Greek letter delta is that symbol right there that we're using for other purposes. So the green one, this is the one that's density. Is that cool? Yeah. Okay. All right. So mass, double integral of density. Now, real quick before we go on to step 2, I want to talk about the notational alternatives. Again, keep in mind, for example, this symbol here, we abbreviate with this, double integral symbol down there. So if we're going to do that eventually, when I rewrite my Riemann sum as a double integral, why can't I just go ahead and do that at the beginning too? Doesn't that seem reasonable? I mean, it's just notation. So with that in mind, what people actually write down day in and day out is this. It's just a little bit more compact and, look, confession, I have not defined this thing right here. Double integral dm, I haven't given a definition of that, but you know what I mean. That's just a shorthand. What it means is this. It means this summation. This, partly developing Riemann sum that I haven't fully developed yet. It's just easier to write it with integral notation. It's very common, it's very convenient, and I encourage, not only do I allow, but I encourage y'all to write things that way. Totally fine. Okay, next. I've got this double integral. Step 2, you see here, is to turn the double integral into an iterated integral. And that part, at this stage anyway, is pretty straightforward. It's the same rectangular domain and the same density, and so it's just a quick rewrite. Hardly anything happened there. All we really have to do is recognize that the range of values of x on my rectangle is the range of values of x for my iterated integral. And likewise, the range of values of y for my rectangle is the range of values of y for my iterated integral. Everybody good with that part? Okay. Right. Let's see here. Last step is the plug and chug. Y'all have already done these. How to take an iterated integral and compute with the fundamental theorem of calculus and get an answer. Yeah, start with the inside, work your way outside, right? So you do evaluate that inside integral. Don't forget which variable is a variable, which variable is a constant. You gotta, keep track of the little details, but it's just the fundamental theorem of calculus followed by the fundamental theorem of calculus. Yes?
So, is the double integral just a way of explaining it conceptually? Because at the end of the day, we just did iterated.
Well, yeah, but you got to look back at the diagram here, right? So this is an essential step, because if you try to make this step, the argument just doesn't make any sense. If you try to take a mass and turn it into an iterated integral, you're going to find yourself saying mass per unit area times length, and I don't know what that means. You know what I'm saying? And so the argument just isn't a thing. You venture into nonsense. And so it doesn't work as an argument. So the purpose of double integrals is to give an argument that actually holds water. Mass is mass per unit area times area. That's fine. That's the intention of talking about mass per unit area. Does that make sense? And then conveniently, again, this is equal to that, and so we're in business. Yes, computationally, in terms of how are we going to get to our answer, yes, the application will eventually be written as an iterated integral. Sure. But again, the answer is not what we're interested in. We're interested in the argument, and the argument requires that we write down the double integral. Okay, yes?
So if the density function was not continuous, we would not be able to do it.
Oh, yeah. Well, that's right. We're not going to worry about non-continuous and, regularity concerns and stuff like that. Yeah, that's a real analysis thing. That's not our problem.
If it's piecewise, though, would we just do two?
If it's piecewise continuous, then you can just break up the domain into pieces on each of which piece. Okay, grammar problems. You need to break it up into pieces such that on each piece the function is continuous, and then it's fine. Yeah. Okay. Right. Okay. Now here's another example. This is just to get another example under our belts, and to show you also how this integral notation is awfully handy sometimes. So sometimes you have to develop the Riemann sum a little bit more carefully. Sometimes there's more involved. Here I speculate about a wall being built in the XY plane where I think of Y as pointing up. So here's my wall. I don't know why my stylus isn't working well. Let me try that again. Here we go. There's my wall. Notice 0 to 10 on the x-axis, 0 to 6 on the y-axis. Right? So this is a 6-foot tall wall that's 10 feet wide. And if this wall is going to be made out of something heavy like brick or stone or something like that, then I can talk about on each little piece of the wall, let's say one particular brick of the wall, how much does that brick weigh per unit area that it contributes to the wall? And here's that given. Suppose we know that, given the density of the material and how thick the wall is, whatever, all that combined, the density in terms of weight per unit area is that function right there. And the question is, it's not how much does the wall weigh. The question is, how much work does it take to build the wall? I've got all these bricks lying around on the ground, and I want to know how much work does it take to pick them up? Now, some of the bricks are going to be lifted not very far. They're going to be lifted just up to here, and that doesn't take much work at all. But some of the bricks I have to pick all the way up to here, and that's a lot more work. Okay, so here's the idea. The development of the Riemann sum. You'll notice I'm using shorthand integral notation. It's just very convenient and compact. The first step is to say the whole is the sum of the parts. Right, all together as I build this wall, total amount of work is, I just have to look at each brick. How much work did it take me to do each brick, and then add up all those little pieces of work. Okay, next, let's focus on one of these bricks. How much work does that take? Well, work is equal to force times distance. I need to know how much this thing weighs. And then I need to know, you know what, let me highlight better than this. I need to know how much does this brick weigh. And then I need to multiply times how much distance did I have to lift it. Right? If I know the weight, if I know how far I had to push against that weight, that gives me work. Work equals force times distance. Is that cool? All right. So how much does it weigh, we ask? Well, I have weight per unit area given. And total weight, I don't have my stylus. I need to get a new stylus. My weight per unit area helps me compute weight as weight per unit area times area. Again, the usual, I need the little pieces. I get to use simple formulas. And weight is weight per unit area times area. Is that cool? So notice I had a kind of a 3-step process here to develop my Riemann sum, but I've got myself a Riemann sum, aka a double integral. But again, don't forget, whenever you see a double integral, that's a Riemann sum. That is a chop it up, add it up computational strategy that we're representing with shorthand notation. Okay, and now it's kind of all over with the shouting. Here's the corresponding iterated integral. Notice that the range of values of x gives me my x bounds. The range of values of y gives me my y bounds. Give me 2 seconds. The only other thing I had to do was to plug in this formula for delta. And boom, we're in business. We've got an iterated integral. Once you've got an iterated integral, plug and chug, answer. Yes, sir.
Work is like force times distance.
Oh, yeah, that's back. This right here, work is force times distance, yeah.
Okay, and the force we're using here, we're saying that's the weight.
Yeah, force is weight.
And I thought you said the density formula was mass.
In this case, I totally know where you're coming from. In this case, we're using a variant idea of density, that it's weight per unit area instead of mass per unit area. This is kind of a units thing. You may be aware, I don't know how many of y'all have had a physics class, but you may be aware that when we talk about the size of objects in the United States, we don't describe them by their mass. We describe them by the force that the gravitational attraction of the Earth applies to them. Which is weird, right? But so something that weighs 10 pounds, well, that's how much force of gravity that thing experiences when it's at the surface of the Earth. But it's actually not mass. Now, there's a easy little relationship there, F equals ma, and this is not what we need to worry about in this class. So in this case, in order to avoid that issue, I've just given the density with that already factored in. And so, the density is given as not mass, but weight per unit area.
So will you know what the delta function is? Mass?
In this case, I'm assuming that the density is given, and then I'm using my knowledge of density to compute the work. I can't say always. Who knows what questions might be on an exam? You never know. But in this case, the density is given, and we're using that to use an integral to compute the total work. Yeah. Okay. All right. Okay. So everything we've done so far has been on the assumption that our domain is a rectangle. For example, computing volume. You want to compute the total amount of volume under a graph. Well, we're computing the volume under a graph over a rectangle. So we're going to entertain now the question of what if it's not a rectangle? What if the volume that we're interested in is over some other region, some lumpy, curvy region like that? Okay, so a little bit of a scary thought. because after all, there's infinitely many different such regions, and oh gosh, it seems like this could change things a lot. Good news, it doesn't change hardly anything. As follows, you want to compute this volume. Can I argue that the volume is the sum of the volumes of the slices? Is the whole the sum of the parts still? Sure. Of course. It doesn't matter what the footprint of your loaf of bread is. When you slice up a loaf of bread, the total bread in the whole is the sum of the amount of bread in each slice. I mean, it doesn't matter what the shape is. Right? When I'm looking at a slice of bread, is the volume of a slice of bread still area times thickness? Yes. Fine. It's not a problem. Can I still compute that cross-sectional area with this integral? Yeah. No problem, because it's still area under a curve, and that curve is still a graph, and it's exactly like before. Hardly anything changes. Nothing that I've made a reference to so far has changed. Notice we still get an iterated integral. Everything's fine. This is super news. Everything's fine. There's one little twist, and only one little twist really that we really need to worry about here. And I'm going to zoom just a little bit so we can see better. That is, notice that these bounds, specifically the inner bounds, right? The bounds for our inner integral are not constants. The inner bounds, you can see, seem to depend on the value of the outer variable. Now, why would that be? Well, let's just look at one at a time. Let's look at the lower bound. Why does, let me do it like this. Why does this x lower bound depend on y? Well, because this point right here, x comma y, that point, you might say, this corner of my slice of bread, right? That corner, where it is, depends on which slice I'm taking. Right? You can see because of the shape of this curve right here, because that is not a straight line, if y were to move, for example, if y were to decrease, then notice that this point moves, and that would then give me a different value. No longer that value, would give me a different value of x. So the fact of having curved edges on my domain, that's what makes this lower bound for the inside integral, the dx integral in this case, right, these x bounds over here, that's what makes this depend on y. Is that cool? And if x depends on y, another way to say that is that x is a function of y. That's it. It's the only thing that changes when you have non-rectangular domains. And then, of course, there's lots of different shapes of domains, and there's cases we have to consider, and good ideas and better ideas and worse ideas that strategically we want to be aware of. But other than details, that's the only thing that changes. Okay. Now, I'm going to point out one other thing further. Again, you look at, here's the y, here's the corresponding value of x, right? We're going in the x direction, is this, and then the point in question is that point right there, and it's defined by this curve, etc., etc. Notice, this whole discussion is taking place in the xy plane. What's happening up here? I wanted the different color again. What's happening up here? How high that point is up above? Who cares? That has absolutely nothing to do with our keeping track of how the bounds move. The relationship between y and x happens entirely in the xy plane. In particular, depends only on the shape of just the domain, only the domain. So arguably, arguably this picture that I've got here then is unnecessarily complicated. this is a three-dimensional picture. And the third dimension, namely up, has nothing to do with what we're interested in terms of understanding these bounds. Yes?
What if the bounds or y are also dependent on x?
But they just. Oh, you're wondering like, what if there's a curve over here too?
Yeah.
Well, then that's just going to mess with how we write our integral. What I'm presuming here is that there is some clear starting value of y and some clear ending value of y, and for a lot of the examples we're going to see, it's just that's the case. And it may be, the nature of the shape of this domain. It could be a lot of different things, but whatever the shape of that domain is, there's usually a pretty clear lowest value of y and a pretty clear highest value of y, and everything else is just somewhere in between there.
You just choose the
Lowest and highest. That's right. Yep.
But if you only have two intervals and your variables are dependent on each other, then how do you, once your final...
We're going to be doing a lot of examples. I'm going to bet dollars to donuts that your questions will be answered by subsequent examples. Is that all right? Ask me again if they aren't.
Yep.
But I think they will be.
Yep.
Yeah. Okay, so big point here. I've got an unnecessarily complicated picture, three-dimensional picture to address what's fundamentally a two-dimensional question. Let's draw the two-dimensional version of that picture. Here's the exact same domain. This curve here, much easier to draw. In the two-dimensional picture, I can find, here's the y value. Here, then, is the corresponding x value. Here is the point that relates them, because that's the first value of x as I look along my y slice. And it's just much easier to see here. So, big win, when you're trying to figure out these inner bounds, don't draw the picture of the application. Don't draw the picture of the volume. It doesn't matter. All we need to know is the shape of the domain itself. Okay, so specifically, I want you to follow the following pattern. When you're trying to find a given bound, first identify the point. Where is that bottom corner of the slice of bread? Right? That point will be on a curve. Identify, if only for yourself, that curve, which of course will also have an equation. Right? So the bound comes from a point which is on a curve which has an equation. And once you have that equation, realize that x, in this case x, because we're trying to find an x bound, x is somewhere in that equation. The bound is just the value of x in that equation, so just literally solve for x in that equation. So that's the process. Bounds relate to points, which are on curves, which have equations. Solve for what you want. Let's see that in action. Okay. Let's see here. Right. So suppose we've got the following triangle, and I want to compute the following integral. Now I'm going to hit the pause button real quick before we go on and go into the details. Wait a second. Where did this come from? What are we computing? Mass or population or probability? What are we doing here? And how do I know that this is the right integral? Well, the answer there is that's just what the question is asking. The question is presuming that you've already got a double integral and asking only for you to turn that into an iterated integral. The question is not about this part of the process, and we're also not going to continue on with that part of the process. This question I want to focus on right now, just this process, this phase 2, right, of the 3-step process. How do I turn a double integral on a non-rectangular domain into an iterated integral that I can plug and chug? But then I'm not actually going to plug and chug. Okay. All right, so that's what we're looking at here. Here we go. Yeah. Okay, so Let's see here. Arbitrarily, I'm going to do my slicing in this order, dy dx, no particular reason. We're going to do the other way in just a moment. But we'll start with this one. What are my x bounds? X. Well, x slices look like this. And, well, my first x slice, let's see, let me draw the actual slices. As I slice in the x direction, those are the actual slices. The first one happens there, where x is pretty clearly 0. I mean, it's the origin. It's x coordinate is 0 at the origin. There's not much more to say about that. I suppose you could say, hey, it's the x coordinate of that point right there, and thus 0. But again, very often it's you don't have to. If it's clear, then it's clear, and that's fine. Okay, the last x slice is over here, where x is 1. Again, why 1? Well, because either one of these points, whether you take this point or that point, either one of them, the x coordinates are 1. So, effectively given. Okay, so there's my x bounds. Now I'm going to fix a value of x. So notice x is now fixed. We're going to look only on that x slice. We're going to ask now for the y bounds. Okay, so the lower y bound, defined by this point. That's the sort of the bottom corner of that slice that I'm interested in. That point is, you'll notice, for every value of x, always on that curve, which has that equation. Keeping in mind, what am I doing? By the way, it's easy to lose track, but I am trying to find a y bound, so I need to solve for y in that equation. Super easy in that case. Y is already solved for, so no effort required, and there you go. That lower bound is 0. I see the process? Okay. Let's talk about the upper bound. Get rid of the stuff here. Let's see here. The upper bound. Again, we're looking only at our x slice, that x slice. Upper bound comes from this point, which is on that curve. Which, if you recall, we're given various points, and you can think about the geometry. That line goes through these two of those points, and so I can do a little algebra, and there's the equation. Again, I'm looking for a y bound, so I need to solve for y in this equation. Again, lucky break, it's already solved for. Isn't that nice? And so that bound is x. What do you think? Everybody see the process there? Okay. Now, you may be concerned. Hey, but I need to solve. How can my answer be have variables in it? I need to solve for the actual value for y there. Well, notice I have solved, because x, being as it is the outside variable, x is a constant for the purposes of that inside integral, and so I have solved for y as a constant. And now it looks, casually, at a glance, it looks like it's a function of x. And for the purposes of the outside integral, it is a function of x. But for the purposes of the inside integral, it's just a value. Okay. All right. Now, we're going to do the same question. This time we're going to do it slicing the other order. Here we go. Other order. Dx dy instead of dy dx. What's the range of values of y? Well, there's my first y slice. There's my last y slice, 0 to 1. I think it's a pretty easy pitch. You can look at particular points, suit yourself. Sometimes I think it's just clear. Now we're going to fix a value of y. We're going to look at that one y slice. And now I got to play the game as usual. How am I going to find my lower x bound? Well, that comes from that point, which is on that curve, which has that equation. Again, easy to lose track of what you're interested in. I'm trying to find x bounds here, so I need to solve for x in this equation. I get my answer is y. That's my lower bound. Again, concerned, am I allowed to do that? Yeah, sure, no problem. Y is the outer variable. Y is a constant. So, perfectly legal. Cool. Upper bound. Let me get rid of the mess. Upper bound for x comes from that point, which is on that curve, which has that equation. Again, keep track of what you're interested in. I'm looking for x, so I need to solve for x in that equation. Already solved for. Sometimes the fish jump in the boat, and 1 then is our upper bound. Everybody happy? Okay. So that's the process. What I've got beyond this, that we'll do on Monday, is just a bunch more examples. But that's the process. So y'all have a great weekend, and see you on Monday. Oh, real quick about the exam. I have finished the scoring of the exam. What I have not finished is the curve and related miscellany. So I'm going to do that before I leave today. So within the next hour or so, you should expect to get some sort of a notification from GradeScope that your grades are available. Please make sure to look at Sakai site first to see what the curve is, right? So I don't want you to look at your score and then use like a high school grading curve to interpret the letter grade. That's not at all how things work here. So make sure you have the curve, right there in front of you, so that when you look at your score, you can immediately see what that is in the 4-point scale. Yeah, you had a question.
You answered my question.
Good. Okay, y'all have a great weekend. See you later. Oh, and don't forget to stick around and make